Welcome back, everyone. This is part 5 in our series on contextual representations. We're going to focus on BERT. BERT is the slightly older sibling to GPT, but arguably just as important and famous. Let's start with the core model structure for BERT. This is mostly going to be combinations of familiar elements at this point, given that we've already reviewed the transformer architecture, and BERT is essentially just an interesting use of the transformer. As usual, to illustrate, I have our sequence, the rock rules, at the bottom here, but that sequence is augmented in a bunch of BERT-specific ways. So all the way on the left here, we have a class token. That's an important token for the BERT architecture. Every sequence begins with the class token. That has a positional encoding. We also have a hierarchical positional encoding. This is given by the token sent_a. This won't be so interesting for our illustration, but as I mentioned before, for problems like natural language inference, we might have a separate token for the premise and a separate one for the hypothesis to help encode the fact that a word appearing in the premise is a slightly different occurrence of that word than when it appears in a hypothesis. And that generalizes to lots of different kinds of hierarchical position for different tasks that we might pose. But we have this very position-sensitive encoding of our input sequence. We look up the embedding representations for all those pieces as usual, and then we do an additive combination of them to get our first context-sensitive encoding of this input sequence in these vectors that are in green here. And then, just as with GPT, we have lots of transformer blocks, potentially dozens of them, repeated until we finally get to some output states, which I've given in dark green here. And those are going to be kind of the basis for further things that we do with the model. That's the structure. Let's think about how we train this artifact. The core objective is masked language modeling, or MLM. And the idea here is essentially that we're going to mask out or obscure the identities of some words in the sequence and then have the model try to reconstruct the missing piece. So for our sequence, we could have a scenario where we have no masking on the word rules, but we nonetheless train the model to predict rules at that time step. That might be relatively easy as a reconstruction task. Harder will be doing masking. So in this case, we have a special designated token that we insert in the place of the token rules. And then we try to get the model to a state where it can reconstruct that rules was the missing piece using the full bidirectional context around that point. And then relatedly, in addition to masking, we could do random word replacement. So in this case, we simply take the actual word, in this case rules, and replace it with a random one like every, and then try to have the model learn to predict what was the actual token at that position. And all of these things are using the bidirectional context of the model in order to do this reconstruction task. When we train this model, we mask out only a small percentage of all the tokens, mostly leaving the other ones in place, so that the model has lots of context to use to predict the masked or missing or corrupted tokens. That's actually a limitation of the model and an inefficiency in the MLM objective that Electra in particular will seek to address. Here's the MLM loss function in some detail. Again, as before with these loss functions, there are a lot of details here, but I think the crucial thing to zoom in on is first the numerator. It's very familiar from before. We're going to use the embedding representation of the token that we want to predict, and we're going to get a dot product of that with a model representation. In this case, we can use the entire surrounding context, leaving out only the representation at t. Whereas for the autoregressive objective that we reviewed before, we could only use the preceding context to make this prediction. The other thing to notice here is that we have this indicator function mt here, which is going to be 1 if we're looking at a mask token and 0 otherwise. And so what that's essentially doing is turning off this objective for tokens that we didn't mask out. So we get a learning signal only from the masked tokens, or the ones that we have corrupted. And that, again, feeds into a kind of inefficiency of this objective, because we, in effect, do the work of making predictions for all the time steps, but get an error signal for the loss function only for the ones that we have designated as masked in some sense. For the BERT paper, they supplemented the MLM objective with a binary next sentence prediction task. So in this case, we use our corpus resources to create actual sentence sequences with all of their special tokens in them. And for sequences that actually occurred in the corpus, we label them is next. And then for negative instances, we have randomly chosen sentences that we pair up and label them as not next. The motivation for this part of the objective is to help the model learn some discourse level information as part of learning how to reconstruct sequences. And I think that's a really interesting intuition about how we might bring in even richer notions of context into the transformer representations. When we think about transfer learning or fine-tuning, there are a few different approaches that we can take. Here's a depiction of the transformer architecture. And the standard lightweight thing to do is to build out task parameters on top of the final output representation above the class token. I think that works really well because the class token is used as the first token in every single sequence that BERT processes, and it's always in that fixed position. So it becomes a kind of constant element that contains a lot of information about the corresponding sequence. So the standard thing is to build like a few dense layers on top of that, and then maybe do some classification learning there. But of course, as with GPT, we shouldn't feel limited by that. And a standard alternative to this would be to pool together all of the output states and then build the task parameters on top of that kind of mean pooling or max pooling or whatever decision you use to bring together all of the output states to make predictions for your task. And that can be very powerful as well because you bring in much more information about the entire sequence. I thought I would remind you a little bit about how tokenization works. Remember that BERT has this tiny vocabulary and therefore a tiny static embedding space. And the reason it gets away with that is because it does word piece tokenization, which means that we have lots of these word pieces indicated by these double hash marks here. And that means that the model essentially never unks out any of its input tokens, but rather breaks them down into familiar pieces. And then the intuition is that the power of masked language modeling in particular will allow us to learn internal representations of things that correspond even to words like encode, which got spread out over multiple tokens. Let's talk a little bit about core model releases. For the original BERT paper, I believe they just did BERT base and BERT large in cased and uncased variants. I would recommend always using the cased ones at this point. Very happily, lots of teams, including the Google team, have worked to develop even smaller ones. So we have tiny, mini, small, and medium as well. And this is really welcome because it means you can do a lot of development on these tiny models and then possibly scale up to larger ones. So for example, BERT Tiny has just 2 layers, that is 2 transformer blocks, relatively small model dimensionality, and relatively small expansion inside its feed-forward layer for a total number of parameters of only 4 million. I will say that that is tiny, but it's surprising how much juice you can get out of it when you fine-tune it for tasks. But then you can move on up to mini, small, medium, and then large is the largest from the original release at 24 layers, relatively large model dimensionality, relatively large feed-forward layer for a total number of parameters of around 340 million. All of these models, because all of them, as far as I know, use absolute positional embeddings, have a maximum sequence length of 512. And that's an important limitation that increasingly we're feeling is constraining the kinds of work we can do with models like BERT. There are many new releases, and I would say to stay up to date, you could check out Hugging Face, which has variants of these models for different languages and maybe some different sizes and other kinds of things. Maybe, for example, there are by now versions that use relative positional encoding, which would be quite welcome, I would say. For BERT, some known limitations, and this will kind of feed into subsequent things that we want to talk about with Roberta and Electra especially. First, the original BERT paper is admirably detailed, but it's still very partial in terms of ablation studies and studies of how to effectively optimize the model. And so that means that we might not be looking at the very best BERT that we could possibly have if we explored more widely. Devlin et al. Also observe a downside. They say the first downside is that we're creating a mismatch between pre-training and fine-tuning, since the mask token is never seen during fine-tuning. That is indeed unusual. Remember, the mask token is a crucial element in training the model against the MLM objective. You introduce this foreign element into that phase that presumably you never see when you do fine-tuning, and that could be dragging down model performance. And the second downside that they mentioned is one that I mentioned as well. We're using only around 15% of the tokens to make predictions. We do all this work of processing these sequences, but then we turn off the modeling objective for the tokens that we didn't mask, and we can mask only a tiny number of them because we need the bidirectional context to do the reconstruction. That's kind of the essence of the intuition there. So that's obviously inefficient. And the final one is kind of intriguing. I'll mention this only at the end of this series. This comes from the XLNet paper, and they just observed that BERT assumes the predicted tokens are independent of each other given the unmasked tokens, which is oversimplified as high order long-range dependency is prevalent in natural language. And this is just the observation that if you do happen to mask out two tokens like New and York from the place name New York, the model will try to reconstruct those two tokens independently of each other, even though we can see that they have a very clear statistical dependency. The BERT objective simply misses that, and I'll mention later on about how XLNet brings that dependency back in, possibly to very powerful effect.